Assalamu alaikum. I'm setting up. I hope it can show. Yeah, that's the last example we did. So welcome once again. Now we did this example in the last video. All we did was, remember, I just remind you again, where are we? We're doing this, we're applying this theorem. And what do you do normally? When you're given some integral, all you need is, you're given the curve, so you need z of t. You're already given the curve in parametric form. So you need this, which will come from here, differentiate, and then f of z is given. So you just apply that. So I wanted us to go, we did example 1, then number 2a, then I want us to go to 2b. 2b is not really done in your book, I just did it. And by the way, just something to point out, this is very important for your exam, because many of you, the book usually doesn't solve all the problems. Many times it tells you to check or solve the problem, finish. Meaning what? If in an exam situation, you answer exactly the same way as in the book, it doesn't mean that you are right, because the book doesn't solve the problem for an exam. When you're solving for an exam, you need to give all the details, and that's what I'm doing for you here. You see, I give you all the details, because when I start awarding marks, I'll say 1 mark, 1 mark, 1 mark, 1, I can count. Very important for exam, note that, okay? Okay, so we continue. Now, example 2b says evaluate the integral. Actually, this example, what I wanted to point out is the following. You see here, we are given the parameter is t. But there are situations where you can actually treat whatever may be, you can treat either this one or this one as a parameter, depending on how the curve is defined. This is what one situation where you're evaluating, this is your f of z, dz, over the curve c, and the curve is this, y equals 5 of x, 5x, where x runs between 0 and 2. You see, this behaves like t. You see, our t in general, when you're defining our curve, our t is like this. So what do? We'll treat now, if it happens like that, then you can treat this as a parameter. What do I mean by that? You express everything in terms of x. You see, we're integrating with respect to t, now we integrate with respect to x. We already know y is 5 of x. So here you replace this with 5 of x. And then now you have, so use or treat x as a parameter. So z is x plus iy. By definition, z is always x plus iy. But then y is 5x, so this is x plus 5ix. If you differentiate with respect to x, because this is now a parameter, you will have dz equals, to differentiate with respect to x, this is 1. With respect to x, this is 5i. So it's just 1 plus 5i dx. That's your dz. And then f of z is just this function, which you already replaced. This part will replace by 5x. So we have the integral will be 8x squared minus iy dz, which is the same as 0 to 2, 8x squared minus 5ix. We replace this with 5x. This is f of z times the derivative of z, which is this. So it's 1 plus 5i dx. Then you integrate. The same thing you just did. You bring the reals, imaginary together. You can just integrate. This is the answer. Check. Okay? Finish. Next is theorem number, now properties of contour integral. So here I can just say, this is something you already know. Why? Because these properties are the same like in real value functions. What do I mean? If you're integrating a function, you multiply by a constant, you can pull out the constant, then you integrate. That's that. If you're adding or subtracting functions and you're integrating, you can, well, here you should also say minus. You can integrate separately. Okay? And then if you're integrating, now this is the beginning, now this is slightly different. If you're integrating over curve C, f of z equals del z. If C can be partitioned into two disjoint curves, C1 and C2, remember that we were partitioning the curve, then the integral of this function can be split into, you integrate over one curve plus integrate over the other curve. And lastly, if we're integrating, now you're going to talk about orientation of the curve. If we're integrating on a negative C, f of z, this is the same as integrating over c of the same function, where minus c has the opposite direction as orientation. Now, when you say orientation, we mean, you see, when you have a curve, you can go this direction or the other direction. Imagine it's a circle. If you go the anti-clockwise, that's a positive orientation. That's what we always take as positive. If you go the clockwise direction, it's negative. So this is what's happening between those two curves. That's that, ladies and gentlemen? Yes. Okay, example number 3. What does it say? Now, this is a nice situation where the curve C, so evaluate the integral, this, where C is a contour shown below. In your book, it's exactly like this. Your contour is, this is C. C is C1 union C2. And now here the way I drew for you is just to say that this is 1, 2, 1, 2, or this is I to I. This is real, this is imaginary. So our curve is this. So this point here is the value of the real part is 1, the imaginary part is 1 also. That's why you have 1 plus I. And here you have, this is 1 and this is 2I. Okay? So our curve C is this C1 union C2. So the integral of this will be you integrate over C1 plus you integrate over C2 of the same function. Okay? That's what we do next. So since C equals C1 union C2, we have the integration over C the same as integration over C1 plus integration of C2. So what is C1? What is C2? Now C1, I want you to remember, what is C1? This is just the line, 1, 1, 0, 0. It means that this line is like y equals x, but x runs from 0 to 1. That's what we have. So this is it. Curve 1 is y equals x with x lying between 0 and 1. So we treat x as a parameter and we perform this integration. So our z, as usual, is x plus iy. Now my hand is getting tired. Z equals x plus iy. So we replace y with x, so we have x plus ix. If you differentiate this, you just get 1 plus I dx. And then f of z, what is f of z? Well, f of z, don't forget what it was defined to be. F of z is x squared plus iy squared. So this you replace with x squared. So this is exactly what's happening here. So you have x squared plus iy squared is the same as x squared plus ix squared. And now you can factorize this is, if you pull out the x squared, you have 1 here and here you have I. Let's integrate. This integration over C1 will be from 0 to 1 f of z, which is, what is f of z? F of z is x squared plus 1I. This is f of z. And what is dz? Dz is 1 plus I dx. 1 plus I dx. Then you can see this is a constant, this is a constant. We can pull them out. We have 1 plus I squared. Then we are just integrating x squared. If you integrate x squared, what do you get? You just add 1, it becomes x cubed over 3. When you plug in the interval, you just have 1 over 3. Now, 1 plus I squared, this is, remember with the 17.1, 17.2. This is 1 times I is I, right? Times, and then you have then I times 1, so you have 2I. Then if you square this minus this squared, you just get this is 2I. So 2I times 1 over 3 is 2 over 3I. So this integral is finished. Okay? Next is now curve C2. What is C2? Well, C2 is just a vertical line. What is this vertical line? You see, vertical line here means that x is 0, so this x equals 1, with y running from 1 to 2. Check. What is C2? Is x equals 1 with y running from 1 to 2. So we treat y as a parameter here. So we have z equals x plus iy. What is x? X is 1, so just 1 plus I. If you differentiate with respect to y, on this side you have dz, on this side you just have, this is 0, to just be I dy. Then what is f of z? X squared plus iy squared. You replace this with 1, you have 1 plus iy squared. You go to the integral, you'll have integration from 1 to 2, f of z, which is 1 plus iy squared, times dz, which is I dy. And so if you multiply this, I goes inside this, it becomes minus y squared plus I, 1 to 2. If you integrate this, this is not a hard thing for you to integrate. You will get minus 7 over 3 plus I. So this is this, and this is this. So you just add the 2. So 2 over 3I plus minus 7 over 3 plus I. So you just have minus 7 over 3. 2 over 3I plus 3 over 3I is 5 over 3I. And that's it. We're finished. Okay, ladies and gentlemen, yes. I think we have energy to look at the next theorem. How much more is remaining? Yeah, we can finish this section. So, the next theorem says bounding theorem. Now, bounding theorem just says that if f is a continuous function on a smooth curve C, and f is bounded by m above for all z on the curve, then the modulus or the upper bound of the function will be the upper bound of the function, which is m, and the upper bound of the curve, L, where L is the length of the curve. So when you're given a problem, all you need to find is the length of the curve and then you need to find where the function is bounded by. Okay? So let's see whether we manage to do this. So find an upper bound for the absolute value of this, where C is a circle, this. Circle center at the origin with a radius of 4. So what do we need? We need the upper bound for the function, and we need the length of the function. Now, a circle, what is the length of a circle? So solution, example 4. The length of a circle is usually the circumference, which is just 2 pi r, right? Or pi times the diameter. So it's just 2 pi, the radius is 4. We already said the radius is 4 in case you have forgotten, is 4. So it's 8 pi. So we found L. We found this L. Now we need M. Now for M, we will need the bound for Ez and the bound for Z plus 1. So how do we do that? Well, the first thing we see is, so next we need to find M, the upper bound for the function f of z equals e raised to z plus 1. That one there. So first note that modulus of z plus 1, this is greater than, actually if I fix this, modulus of z plus 1, if I just hide this, I can say this is greater than modulus of z. A modulus of z, is that nice? Yeah, modulus of z is smaller than this. If I subtract 1 from modulus of z, I still get something smaller. So this is greater than modulus of z minus 1. But modulus of z, because this is 4, so this is 4 minus 1, which is 3. So modulus of z plus 1 is greater than or equal to 3, which means if you take the reciprocal, because it's positive and this is positive, you divide by, my goodness, and this line should not be here. So if you take the reciprocals, it means that you reverse the order. So this means 1 over modulus of z plus 1 is less than 1 over 3. That's one relation. So we found some relation for 1 over z something. The next thing is e raised to z. Now e raised to z modulus is modulus of x plus iy, because z is x plus iy. And now this is just modulus of e raised to x, e raised to power iy. Now, if you take modulus of e, well, this is the same as modulus of this times modulus of this. But modulus of this is e iy. What is e iy? Is this kind of thing. Let me show you where. This kind of thing. EIT, so it's cos y plus I sin y. Modulus is just c squared plus z squared, which is usually 1. So it turns out that this is just 1. This is 1, so this is e raised to x. So this equals e raised to x. Okay? And then now, well, modulus of z, the circle, I just wanted to show you how does the circle look like. This is a circle. Which means the maximum value of x will be when y is 0. So it will be 4. So that means e raised to z, which is e raised to x, this will be at most the highest value is e raised to power 4. So that means we found m. Our m is e raised to power 4, which is for the numerator, and for the denominator is 1 over 3. So this is our m. Hence, the bound for what we were asked to do is ml. So it's just this number times this number. So it's just it's this number times 8 pi. So it's 8 pi e raised to 4 over 3. And that's it, ladies and gentlemen. Congratulations, you have finished this section. So next is 18.2, which we'll do in the next video. See you shortly.